The following video is intended for general audiences. It may contain coarse language, bad puns, suggestive images, and bad advice. It probably just contains retro computer crap. But don't try this at home, even if I tell you to.
Okay, hi. So I just want to do a quick demo video showing the UberGrom configuration tool. It's released, it's on my website along with the full package, all the source code, and everything else you need. The idea being here is that what we originally were going to do was to package the AVRs with the firmware, and then people could just program them right on their TI. Right now, people are not doing it that way, and they're also complaining about how difficult it is. So I hope this helps a little bit. Anyhow, the idea here is that you load the UberGrom firmware onto your AVR. You don't have to load any TI software or figure out packaging. Just load it on the AVR, plug it into your cartridge board, plug your board into the TI. When you're powering up the first time, hold spacebar. Before you get to the title page, just as you power it on, hold spacebar. And that will load a little recovery program. Now, I mention this because I don't have that emulated in Classic 99. So in Classic 99, in order for me to get a way to load the config tool, I replaced TI Basic with Editor Assembler Complete. In your case, you're going to hold spacebar when you power up, and you're still going to see TI Basic on this screen, but you'll also see EasyBug and Run Program File, which Run Program File is what you're going to want. That's just a little different because I haven't finished the emulation in Classic 99, and I will, when I actually have a project to use it. So anyway, either way, you're going to end up here. And just go ahead and just run it normally. If you have a RAM disk or whatever that takes up on boot, you can run it from there too. And here we go. So it's just comes up with this basic little tool, and there's three main parts to this tool. This is the current view of the cartridge from the TI's point of view. So it covers the GROM base, and it covers the 5 GROMs that are mapped at that base. And I call these slots because you can program things into these slots. Some people call them GROMs, some people call them whatever else, I don't care. In my terminology, in my documentation, they're called slots. Now, the way that the system works, you'll notice that 0, 2, and 4 are not listed here, and that is because those are the operating system GROMs. 0 contains your basic OS for the TI, and 2 and 4 contain TI Basic. It is possible to override them with an external device like this or a graham cracker or whatever else, but because the UberGrom is specifically intended to be used in cartridges, and because I have other projects that I'm going to release based on similar technology, I wanted to not have this be released with the ability to overwrite the console GROMs. The reason being is if you plugged a cartridge based on this technology overriding the console GROMs in, and my later project, which will be the multiple personality distorter, plugged in at the same time, you'll damage one or the other because they're both TTL devices and they're both going to try to talk on the bus at the same time. It's not a good scene. So better to leave it locked out just for safety's sake and say that this is a device for making cartridges, which is what it is. It's for making cartridges, as Gazoo has done to great effect already. So the concept of a base, this is the address port, or the address in the 9900's memory map that it talks to the GROMs at, the base address. And the console allows for quite a number of different bases. There's in fact room in the memory map, according to Terry Nespiekel's page, for 256 bases, each containing 40K of GROM, which is pretty darn good. The console itself only checks the first 16 pages, and just because of number of I/O pins, that's how many we went with the UberGrom. So over here is your help window, and this will vary depending on what you're doing, but usually it'll show this list, and I'm going to go through that shortly. Down here is a Hex Viewer to show you the memory of what you're currently looking at. Right now it's empty because we haven't selected something yet. It's important to note this is a viewer and not an editor. You have to modify your files offline, not in this program. Alright, so the first thing that would come over here is these are the arrow keys, so you have to hold function when you're pushing them. The first one, left and right to change the base, and that's here. So if I just hit left, right, you'll see that it cycles through the bases. Now right now they're all empty except for the very last base. The flash device is mapped at E. And I'll cover what the devices are later. This is necessary for this tool to function, however, because this is an expectation of this tool that enables it to actually write your code into the UberGrom. And that can be disabled, but it would be the very last thing you do. Luckily, there's more available slots than devices, so hopefully that choice won't ever cause a conflict for somebody. Up and down scroll viewer, again, these are arrow keys, and I'll show you that when we actually load something in there. The next option is select viewer. Select viewer is not going to do us any good yet because we haven't actually got anything to view. In fact, I'm going to stop going through this list because doing so before I load something is pointless. Let's say you want to start mapping things, and we're just going to start right here at the base of 9800, which is the default, of course. 68AEC, well, let's start right at 6000. And what I've done is I've prepared a small list of files that we could try to load. Let's see if I can get that to pop up. There we go. So, demonstration cartridge, my PSG mod demonstration tool from years back, RXB GROM, and editor assembler GROM. So what we'll do is we'll build a cartridge that has all of these loaded at different GROM bases, and that will make review module library work so that we can toggle through them. And I'll just show you how that works. Now there's one gotcha, and I'm just going to mention it right up front here, and that's RXB has a ROM portion as well as GROM. This is GROM only, okay? So for the ROM portion, you build that the way you've always been building ROM cartridges back in the day. You build up your EEPROM, you plug it into the board. For the sake of this demonstration, I'm assuming that's already been done and that the board is physically ready to roll. Okay, good. So the next thing we got to do then is load something. So let's start simple, I guess. Let's put I think my PSG mod tool might not work at random bases, but I think everything else here does. So let's go ahead and put mine in the first base. So that is a thing that matters, right? With GROMs, the address matters. Most of the time the base doesn't matter, but the address always matters. There's a couple where the base does matter. Some things, I'm trying to remember now, I think Parsec had trouble if it wasn't in base 0. Okay, so anyway, to load something, select the address you're interested in. We'll start with 6, which represents 6000. And you'll see this little pop-up here. Select GROM, 15 banks available. EEPROM, there's only one because there's only 4K of EEPROM. I/O, this maps all 4 or 6. I can't remember right now, and I don't have a board in front of me. GPIO pins are mapped to this area address. ADC, there's 4 analog to digital converters on the device, and you can map each one to a separate slot. There's one high-speed Uart with 256 bytes each of send and receive buffer. Very useful if you want to communicate with other devices. Remember, it's TTL, so if what you're talking to is not a 5-volt serial device, you need some kind of converter on your board. Flash is the flash controller, which I touched on earlier. It's direct access to the flash and lets you rewrite the GROM portion of the device. You probably normally won't want to use it because if you have data to save, you would just use EEPROM, which you can write to as if it was GRAM. Except that it's slow, very slow, even compared to GRAM. Timer is just a continuously incrementing high-speed timer. I think it's something like 16 kilohertz, but it's in the documentation. There's 2 pages of RAM. One is 8K, one is 7K, because there's 16K RAM on the chip, and I needed a little RAM to run the emulation itself. And none just lets you delete whatever's currently mapped there, of which there's nothing. So just to map a device, all you do is just select it. So if I hit E, EEPROM's now mapped. And you notice there's some values in the EEPROM already, and they've shown up down here in the viewer. And I can scroll through the viewer, just arrow keys up and down. So if you check the documentation, the first, I think it's 120 bytes of the EEPROM are reserved for this mapping table here. You can get some of that back if you need more memory, but with 4K of EEPROM, I think you're pretty good. Just always work past that point. The other thing to remember about EEPROM is you can read-write it as if it were GRAM, that's fine, but besides watching out for this space, remember that there are limited writes. It's like 100,000 erases. So whatever you're writing, there's 2 rules you want to apply. 3 rules, actually. The first rule is never write if you don't have to. So always read the value, and if you're going to write the same thing, don't write it. Just leave it. That reduces wear. Second thing, it's going to fail. Expect that. CRC your code. Make sure it's valid. And finally, if you can afford to, load leveling. Don't keep writing to the same places over and over again. The intent of this device is once you've set this up once for your cartridge, it's never modified again. So consider that sort of thing for your application as well. Either spread your writes out, block it out across the entire 4K space, or don't write to it all the time, or something like that. You can and will wear it out. Okay, and now that's shown off how the viewer works, which is very handy. Let's go back here. I/O, you won't be able to see much here in the emulation. The first 64 bytes are reserved for all the hardware devices. The reason for this is just to make that's 32 bytes. The reason for this is just to make the console not accidentally trigger review module library if you happen to map an I/O device in a spot it's looking at. Usually review module library you'll only want if you actually have multiple pages of actual cartridge data. There's 6 GPIO pins, might be 4, but I think it's 6. You can program and configure them according to the documentation, and each of these bytes represents the status of the pins. ADC, there's 4 ADCs, and the idea of this is you select it and then you say which one you want, 0 to 3. I'm just going to say 0 for now. And this is an actual analog input pin with a range of 0 to 256 on the device. And there's 4 of them. The read speed is not fantastic because you are limited by the speed of GROM reads, but it's not too bad, and it's a flash conversion, so it should always be accurate. If you need a way to read an analog input, like say an analog paddle or something, this will give it to you. No worries at all. Besides, I don't think there's any configuration at all. I think you just read. And the idea being that you can just continuously keep reading the GROM for the full, 6K space, and only have to worry about wrapping the address every so often, which saves you a lot of time of having to reset the GROM address if that's all you're doing. Uart is reasonably complicated. This is a high-speed device. It's easily capable of 19,200 BPS. But it's 5 volts, as I mentioned earlier, so be aware of interfacing issues. And it's got 2 buffers of 256 bytes each, which can be fairly quickly overrun. So take care in your code. Make sure that the device you're talking to either stops or you're running it slow enough that the TI can drain those buffers and keep up. There's status bits and configuration bits and all that stuff. Check the manual. Flash device, I'm not even going to go into detail on, but the basic concept is this is a direct interface to the AVR's flash controller, which means that you set an address, write 512 bytes of data, and command it to write. It's that easy. This tool does all that for you, however, in theory, most people won't ever need to. Timer, continuously incrementing timer that just keeps running. It's 16 bits wide, so you can keep reading it. It has functionality that you can just read the least significant byte continuously if that's all you care about. It has no specific purpose. It just runs forever. You can't reset it or anything. But it repeats through the memory space again for the sole purpose of allowing you to just keep reading without resetting your GROM address continuously. RAM, so there's 2 pages of GRAM. The second page is only 7K long instead of 8. And nothing special about it. You can read and write it as per normal. It is RAM, of course, so it's lost when the system is powered off. Unlike EEPROM, which is preserved. However, unlike EEPROM, this writes much more quickly and does not have a wear problem. And none, which of course does nothing. Let's go ahead and start setting up that cartridge I was talking about, because I think I've talked for, what does this thing say, 13 minutes already. You're probably getting bored. I don't really care if you're bored. I'm having fun. So, DROM, 0 through E. So this is kind of a bit of a trick that you have to sort of wrap your head around. So the AVR has 15 pages of GROM. Each one is 8K. And it's just a linear bank of GROM, right? The TI has this base slash address or slot or whatever you want to call it concept. And the two of them sort of intermingle with each other in this system. But the basic concept is you load memory into the AVR and then you map those pages to the TI. This is making us do it in the inverse order, and that's just the nature of the interface. You can blame me, you can curse me, but it's not that hard to figure out. So basically you decide what your map's going to look like first, and then you load your data. So I'm just going to go ahead and do that. So I remember I have off to the side here, I said my PSG mod was going to go first, and I can see that it is 4 GROMs long, and I know that it starts at 6,000. So I'm just going to go ahead and say, okay, so GROM 0, GROM 1, GROM 2, and GROM 3. So there's 4 pages reserved for my PSG mod. And you can see that there's actually some memory currently loaded in the AVR's memory. You probably won't see this, but you might. This is just leftover data, and we're actually going to override it. I guess my emulator was loading some code, and I thought that was turned off, but no big deal. So I'm going to do this one base at a time because it's easier to keep track of. You could also just plan your whole thing out on paper first, and then you can just go, do all the mapping, do all the loading, whatever you like. Let's go ahead and load now. So the first thing you do is you do all your loads and saves through the viewer. So the first thing we have to do is select the viewer so that we know we're looking at the right thing. So we go V, and it's like, okay, well, which one do you want to view? And I want to view 6. And it reminds you here that it's looking GROM, that this is currently mapped to GROM 0, as in up here on base 9800. And there's currently nothing here, but that's fine. So now we hit load, and it's like, okay, well, what file name do you want to load? If you ever make a mistake, function 9 works on most screens, just to say. All right, so it's on disk 1, and it should be EPSG mod G1. And now it's saying, well, should I skip the GRAMCracker header? And this is something you have to know. Is there a 6-byte GRAMCracker header or not? This tool will skip the header for you, but it will not attempt to parse the header because I didn't want to go through the trouble of trying to figure out how to automatically find a spot in AVR memory to set it and then try to figure out the map. You can do that yourself. It doesn't take very long. In this case, I know that there's no GRAMCracker header, so I'm just going to say no, and it's just going to load the full memory directly in. And then it programs it immediately, and then it shows it. Now here's how we know we're right on the GRAMCracker header. We look at the first few bytes. So we know that all cartridges, valid cartridges with a header, need to start with AA. There are sometimes GROMs that don't start with AA if they're just data and they don't contain a header, but most of the time they will. And in this case, it does. So we can look at that and say, yeah, that's a valid header. We know that's right. That actually won't be true for the other 3 files in this because they don't have headers, but it's like I say, it's something you sort of know. If there was a 6-byte header, I've got an example that's going to come up later, and you'll see what that looks like. All right, so let's go ahead and load the rest. So going to go viewer 8, load, disk 1, EPSG mod 2. No, it did not like that. Did I type it wrong? Probably. I'm just going to try it again. Disk 1, EPSG mod G2. There we go. All right, there's part 2. So view A, load, disk 1, EPSG mod G3. No. And view C, load, disk 1 EPSG mod G4. So one thing you may have noticed is that I had to load each one individually. This tool doesn't support concatenated GROM images. You've got to split it up into 8K chunks. And for my purposes, I just use the Linux tool split. It's pretty easy. There's Windows ports. You can take care of that. It's not too hard at all. All right, so now if we take a quick look, so here we have everything loaded. This is mostly empty because this is a partial file. It didn't have much in it. View C. Doopy-doopy-doo. Oh, we're already viewing C. View A. There's a pile of data there. Yay. This is all music data anyhow, so I don't know what I expect to see. But sometimes it's fun to just browse. Whoop, I did something wrong, so escape. No changes. Viewer 8. Yep. And viewer 6. Should at least be able to see the menu in here somewhere. Anyway, I'm wasting time. It doesn't matter if we can see that. Okay, so basically, this base, finished. Cool. We could test it. but I feel brave. Let's move on. Also, I sure hope YouTube still lets me upload long videos. Had some trouble with that Perform This Way TI conversion I uploaded. Switch over to next base. Now we're at 9804. You can see it's all been cleared out. And on this base, let's put demonstration. And I'm just going to whip through the same thing again, right? So viewer 6. It was already saying 6, but you want to be sure. Sorry, there's nothing mapped yet, so can't load because there's no. What happens if I try to load? No memory mapped. Ta-da! Just for what it's worth, you can also load data into EEPROM. Be aware that it will screw up your mapping, so you'll have to redo the mapping after you load it. Just a point of reference. There's also the save file, which lets you save whatever's currently in the viewer. That lets you save all GROM files and also lets you save RAM. I figured that might be useful if you're debugging something that uses GRAM and you want to just get a dump of what's in there. You could just function quit out of your application, load this up, save RAM, and you have a nice, neat little file you could analyze. Of course, RAM is lost if you power cycle. Okay, so I know that I went 1, 2, 3, 4, right? Sorry, 0, 1, 2, 3. So we're just going to go ahead and we'll put the demonstration module in 4, 5, 6, 7. Looks like it's 4 as long as well. So 6, GROM 4. Now let's say I screwed up and said 3 because I couldn't remember. 6, GROM 3. We're going to look right here and say, oh, yeah, that's already loaded. Right. So 6, GROM 4, 8, GROM 5, 8, GROM 5, A, GROM 6, C, GROM 7. And this is where it's kind of handy to have written all this down in advance, of course. And I'm just checking to make sure I've got enough slots. Yeah, okay, good. All right, so now we're just going to go ahead and load these ones up. So this is the demonstration module. So load, oops, always view before you load to make sure you're loading where you expect. Notice I was on the wrong one. So view 6, load, disk 1, demo G1. Wow, that didn't work. Demo G1. Nope. And we check, and there's our header just like we expect it. So view 8, load, disk 1, demo G2. It is really helpful, by the way, to have all this stuff written down somewhere so you know what you're doing. And you can see the glad you decided to stay. Here we go. All the lovely text of the demo cart. Load. Fart. Sorry. Anyway, view A, load, disk 1, demo G3. You know what's really funny is I think I remember trying this previously and that my demo ROM was corrupt. Hopefully it'll boot, because otherwise this is going to be a pretty screwed up demo. And I'm not doing this video again. Alright, anyway, where was I? View C, load, disk 1, demo G4. No. Alright, now there we go. Demonstration's loaded, and we're done with this bank. So we got 2 left to go. We got RXB and editor assembler. I'll do RXB next, and it's actually 5 GROMs long, so it's the full thing. Look, I said GROM. Hey, I get a point. Alright, so I'm just going to go ahead and do the mapping first. I can't remember where we left off, so let's look back at 4, ended at 7, so the next free one will be at 8. So 6 GROM 8, 8 GROM 9, A GROM A, remember hexadecimal, C GROM B, E GROM C. You know, it is easier to say GROM. You might have convinced me, Tony. Anyhow, so now we go ahead and load them. So viewer 6, load, sk1.rxb2001g1. I don't have your new one yet, Rich. Graham cracker header, no, and we check, and there's our AA, so that's good. View 8, load, sk1.rxb2001g2, no. View A, load, k1.01g3. Alright, view C, load, disk 1, RXB2001G4, no. And view E, load, ESK1 RXB2001G5. No. And there we go, RXB. Oh, look at there's our menu. Ah, cute. And this one has the power up header, or a header in it. Sorry. So I changed page here, and of course there's nothing on E. It's blank, so that's why the viewer went blank. Go back over here. So view C, yeah, view A, view 8. Oops, I accidentally selected something. Escape. Sorry, function 9. View 6. All right. All looks good. So 633B. Wow, the header's pretty far down, eh? There it is. Anyhow, yeah. So that one's done. One more. So this time we're going to load the last one. The only thing we're going to put on this page is Editor Assembler, and this is the TI version of Editor Assembler. So we go to map 6, Grom. What was the next one? Well, they don't have to be continuous. Let's just put it at E. So that's the last one. That leaves a gap because the last one was C. That means there's going to be nothing in D, but it doesn't matter. You don't have to map everything. You don't have to fill every slot. Okay, so view 6, just because you always want to do that before you load to avoid mistakes. Load sk1.tieag. Skip header, of course not. And oh, that's funny. This doesn't look like a proper header, does it? And this is where I told you we were going to discover one. So the GROMCFG header is 6 bytes long. I may have gotten these demo bytes that I snuck in here wrong. I can't remember the exact syntax, but there's like a flag for more files, there's a load address, and there's a length. And then the cartridge begins. And in this case, we know there should be an AA because this is Editor Assembler, for crying out loud. You can always look at your file if you're not sure. So, okay, I screwed up. There is a GROMCFG header on this. No big deal. Load. Load it again. tieag.bin. Oh, what am I doing? .bin. tieag. GROMCFG header? Yes. Now, of course, it doesn't read the GROMCFG header. It just skips it. That's important. But now you can see that's more like it. That's starting where we expected to start. So, good. Now we have everything in here. The chip is actually programmed. It's fully programmed right now. You could just hit quit, and off you go. In fact, well, before we do that, I want to finish demonstrating the tool here. But you could just hit quit, and you're done. But usually you want to back your data up in some way, and that's where the next step comes in. So let's say you want to save it. Again, it works on the viewer down here. So, okay, we're just going to say save viewer. Enter a file name. I'm going to have to save to a different disk because I'm using a disk image here for my load, so forgive the fact that I have a disk 0. That's my fallback. And I'm just going to call it EA dump because that's what I'm dumping. And it's like, skip GROMCFG header? It's kind of a poorly worded question, but basically it's saying, if you say yes, it'll write the raw file exactly as in the viewer. If you say no, it will write a dummy GROMCFG header, which I think is always the 6 bytes I showed you. That header will probably be wrong for a real GROMCFG. It's your job to go in and fix it. It's just sometimes easier to modify bytes than insert new ones, so it's here just to make your life easier. 9 times out of 10, you're going to say yes. Okay, and you can't see anything, of course, but if we bring up the Classic 99 debugger, we should see that it successfully, here we are. So it's saving from VDP, disk 0 EA dump. And so it has written the file. So it's a program image file. It's 8K plus 6 bytes, and it's ready to go for whatever you need to do. Now, even if the original GROM was 6K, it's still going to dump 8K. That's just the way this tool works. You have to know what you're doing with if you want it to be exactly the right length. Great. Okay, that's fine. But what I just did took like 15 minutes. I mean, who the heck wants to spend 15 minutes every time they program a new cartridge? That's lame, man. You're lame. All right, fine. So the little caret symbol here means control, and we have load device and save device. And these do just what they say. They load and save the entire UberGrom image, excluding the AVR firmware, of course. We'll get to that later. And so you could, now that we have it all configured, we're just going to save the device. It's going to write out this 124 plus K file containing everything. All the GROM flash and all the EEPROM and the configuration. and it's just saved into a DF128 file. It's easy to look at and modify if you need to, and you can just load it right back. So let's go ahead and try to save this. So this will save the entire device and all configuration. It will require approximately 124K, and it warns you here that means no single-sided, single-density disks, because those are only 90K. I don't think anybody is still running single-sided, single-density disks. If you are, I'm sorry, you can't save an UberGrom on your floppy disk. Anyhow, so great. Okay, am I sure? I am sure. Hit yes. I'm going to save to disk 0, big dump. This is kind of a meaningless counter. It's just I needed a counter that went higher than 10, so I used letters. And it gives you an indication that it's working. On a real machine, you can expect this to be slower. Writing to a PC hard drive is, of course, pretty fast. All right, so just to bring up the debugger again, and what you'll see is here it is writing the end of the file, and then closing the file, and then some UberGrom debug that you don't need to worry about right now, unless you're going to be programming it, which you can talk to me if you are. Or read the manual, because it's all in there. Okay, so great. That's all done. It is saved. It is ready to go. The last thing I need to talk about before we see if it worked, and for the sake of this massive video, I hope it worked, is F7. So function 7 gives you a little advanced menu. This is where you can tweak some of the options of the GROM without needing to know all the exact addresses in there. So the first one is bases, Control B. So you can turn bases on and off with Control B. Bases are, of course, this. If you turn bases off, then the only base that exists as far as this device is concerned is 9800. If you try to read or write other bases, it responds to all of them. In other words, it's going to work exactly like a standard TI GROM in the console or in a normal cartridge, and just completely ignore the base, and the first base 0 will respond to everything. This is for people who don't want to deal with the extra memory or have some other specific requirement. I don't envision it being used very often. It reduces you to having just 5 slots available because you can't use the other bases. And it does give you one advantage, and that is that your EEPROM system usage goes down to like 16 or 18 bytes. I don't think most people will use it. The last trick to note, though, is if you turn bases off, back is now prohibited. That means I can't go back into the rest of the application. The reason is that this application needs bases working in order for the flash system to work. So if you wanted to turn that off, you would do that as your last step. You would set it, and then you would quit and get out. All right, recovery. So the way that you got in here, if you were following my instructions earlier, is when you powered up your TI, you hold space. So the UberGrom has this concept. Hold spacebar, turn on the system, and it inserts EasyBug and run program file into the startup menu. It does this by overwriting one of the very last banks in the very last base, and it only works on first boot. Any reset after that, including hardware reset, will not work. It has to be from power off. And if for some reason even that limited recovery doesn't work for you, for instance, maybe you're releasing a product and you don't want other people to be able to do that, you simply toggle that off and it won't do it. It's that easy. Rollover. This lets you basically run the GROM address bus between GROMs. In the original system, GROMs are 13-bit devices with 3 bits of select. What this means is that if let's just say you're doing a massive move inside GROM, the GROM at 6000, right? And I have a little difficulty explaining this because I strongly opposed this option. Nevertheless, anyhow, so you're reading, and you want your read to just keep on going. When you hit 7FFF, you want it to roll right into 8000. On the hardware that is in your TI console, that will not happen. It will wrap back around to the beginning of 6000 and stay within that one chip. This is because the address bus, like I said, is only 13 bits internal to these chips, so it can't wrap those upper 3 bits. If you turn rollover on, then it will roll over from one to the next. The downside is that means that the UberGrom's concept of the system address is now different from the rest of the computer's concept of the system address. You probably won't have too much trouble with this. GPL very rarely relies on increment of the GROM address. It's one of the reasons it's so slow. Um, in fact, the only case I can see for this actually working or actually being needed is if you were reading GROM from assembly language. Nevertheless, this is actually how the graham cracker and similar devices worked. They didn't bother emulating the 13-bit address bus. They just created a 16-bit one and let her rip. So if you really, really need it, you can turn it on. The limitation in the UberGrom is it will not let you roll the address over into the console GROMs. For instance, if you're at FFFF, it will not let you roll over to 0. And this is just to avoid conflicting with the real GROMs that are already there, again, for my future projects. This should not bite anybody. If you find it's biting you, turn it on. Be my guest. Finally, flash device. And this turns it on and off. This is the flash device mapped. Oops. Let me go back. Oh, wrong key. Let me go back. Let me go back. There we go. This is the device mapped on the very last port. Flash. You'll see that it's also mapped in the EEPROM device. That was just a temporary thing the tool did. You probably should leave these last two alone in most cases. Anyhow, so come back into here. If you turn the flash device off, it doesn't update the screen because we haven't gone out of the advanced menu yet, but we're not allowed to either because the rest of the tool needs the flash device on. All that does is delete it from here so that, if your cartridge doesn't want the flash device to be mapped anywhere in memory, maybe you have a habit of randomly scribbling through GROM and don't want to somehow accidentally trigger it. Turning it off will prevent it from ever firing. Okay, last thing you do, you would hit quit. All right, good. So, that said, our device is all built, backup is saved. Let's see if it worked. Hey, PSG mod and review module library. 3. Demonstration, review module library. RXB, review module library. Editor assembler, review module library. Hey, shall we see if any of them work? I think so. Ooh, this looks promising. Ta-da! Yay! Oh, this is old stuff. To be honest, I like the BGM stuff a little more now, but it's okay. This was awesome when I first heard it. Okay, so enough reminiscing. Let's try the next one. Review. Demonstration. Look at that. Looks like it's going to work. Ta-da! I don't think anybody really wants this. Oh, I'll run it to the logo. Hello, I'm the Texas Instruments. Review. Alright, let's see if RXB boots. This is going to be the most questionable one because I'm not sure I set it up right. I didn't test in advance. Ba-da! Huzzah! Great, great. And we're in. Bye! And just for kicks, we'll load editor assembler. Watch out because review module library moves on that screen. There we go. We have successfully programmed an UberGrom. We've got 4 bases working. We've got 4 programs in it. And everything is hunky-dory. But, of course, there had to be a but because, this video is already 40 minutes long. Luckily, the but is short. What if you got a fresh one? And I'm going to attempt, hopefully this won't kill the recording. Okay, it looks like it went black. New. There we go, okay. So, new Classic 99, UberGrom is, well, it's actually not blank, but it's certainly not loaded. So, I'm just going to demonstrate loading that file we saved. Alright, so it's got some, this is my default configuration that's, the emulator supports. If I actually show you one of these, you'll see it is not what we loaded. In fact, it's mostly zeros. Alright, great. So, load device. This will overwrite the entire GROM and all configuration. Are you sure? I am not sure. Yeah, I'm a coward. Okay, we're going to do it. Yes. And it was disk 0.bigdump, was that right? And there it goes. The file format for the DF128 file is in the documentation. It's pretty much a straightforward raw dump, with the exception that the configuration space of the EEPROM is saved after the rest of the EEPROM, and that was just so that I could write the configuration space regardless of whatever the mapping was. Alright, so we take a look here. We see the PSG mods loaded into first base. Second base seems to have demonstration. Next base seems to GROM 8. Oh, that's funny that it jumped there. Load viewer 6. Oh, no, that's right. What did we stick on this page? Oh, RXB, right. And editor assembler. Huzzah! And if I quit, there it is. That's it. Control L to load. Alright, thanks for watching. Hope you made it through the whole thing. Have a good one.